One example of SuperTwin's flexibility in real-time event monitoring is the LiveCarm dashboard. SuperTwin is able to combine various performance events and perform computations on them to observe even complex live performance models. In this case, one of the automatically generated dashboards by SuperTwin is a live cache-aware roofline model, which can be used for intuitive application performance profiling. The real-time metrics used by this model are the arithmetic intensity and gigaflops, which are both calculated in real time by complex formulas derived from the performance counters of the target system CPU. The static lines themselves are based on the stored results of the CARM benchmarks that are previously automatically configured, ran, and measured by the SuperTwin tool, allowing us to plot the performance of our applications relative to the limits of the system we are running them on in real time. This is great for profiling heterogeneous apps that can have different execution phases with different bottlenecks that need to be addressed in distinct ways. The diagnosis of these issues becomes easier when we can take advantage of the optimization hints that the CARM model is able to give us. So I'll now quickly show you this dashboard in action in my local machine while running an SPMV algorithm on an original matrix versus an RCM reordered matrix in order to observe the performance impact of this reordering method in the SPMV execution. So here it is in my local machine, the LiveCarm graph. Besides the LiveCarm graphs in this dashboard, we also have some performance event data, along with an info card of the target system CPU. In this case, we have floating point scalar and floating point 256 double instructions, which are actually AVX2 floating point instructions, and total memory operations being displayed. So right now my system is idle. As you can see, we don't have a lot of movement here in the graph, but I will now start up an SPMV algorithm implementation, in this case Intel MKL SPMV on an original matrix, and we should observe some interesting movement in the graph. So as you can see here, we have some dots showing up. Okay, so as you can see, we are around this area here. These ones were from transition phases at the start. Sometimes the readings can be unstable, of course, because this is real time. So as you can see, we are around this area in terms of performance. And I'm now going to switch over to the RCM reordered matrix and show you how the dots will move up and to the right as we get a better arithmetic intensity and more gigaflops. So all I did was stop the other execution and start it up again using the RCM matrix. So now we have a little bit of downtime between the reading, but we should now see our dots in a moment, and they will be substantially higher. And so as you can see, this resulted in about a twofold improvement in the gigaflops department and a slight improvement in the arithmetic intensity, which shows us that the RCM reordering benefited the algorithm very much. And actually, since it finished very quickly, you can also compare that the program measured this amount of gigaflops, which is quite close what we are measuring here. Of course, we have system noise, but as you can see, most of the dots stayed around this 1.3 gigaflops area, which shows you that our LiveCarm can be accurate even with real-time readings. So this pretty much concludes my presentation, and I thank you for listening, and have a rest of a good day.